Hello everyone. In the previous lecture, we have studied about spherical refracting surfaces. In this lecture, we will study about lenses. So to begin with, a lens is defined as it is a piece of transparent refracting medium bounded by two surfaces out of which at least one is spherical. So it will have a transparent material and that material will have two surfaces out of which at least one is spherical. That is called as a lens. As given here, the lenses are of many kinds, but the most common types of lenses are called as biconvex lens. Here, bi means two. So it has two convex surfaces. As seen here, this is a convex surface and this also is a convex surface. So this part is transparent. In this case, both the surfaces are convex. Hence, it is called as biconvex. But by convention, is simply called as convex. So whenever I say convex, it means it is biconvex only. Out of these two surfaces, if one surface is plane, example, if this surface is plane, then it is called as planar convex as seen here. But if this surface is plane, then we get something of this kind. Even this is called as planar convex. The next type is biconcave. We saw in the previous class that a spherical refracting surface is called as concave or convex based on which side is facing the rarer medium. In this case, since the convex side and the convex side are facing the rarer medium, because surrounding the lenses are mostly kept in air, which is a rarer medium, and lens is mostly made up of glass. Hence, since the convex side and this convex side are facing the rarer medium, this is called as biconvex. Here, this is a concave shape or concave side, and this also is concave side. Now this concave side is facing the rarer medium. Here also this concave side is facing the rarer medium. Hence it is called as biconcave. Now out of this, or simply concave, out of this, if any one surface is plane and other is concave, example, if we look this as plane, then what we get is this kind. This is called as planar concave. Instead of that, if this surface is plane, then what we get would be something of this kind. Even this also is called as planar concave only. As you learnt in your high schools, the most common type of lenses are called as convex and then concave lenses. A convex lens is called as a converging lens and a concave lens is called as a diverging lens. So a lens of this kind is called as a convex, which means biconvex only. Now for a biconvex lens, its center, middle part would be thicker, and as we go away from the center, the edges would be thinner. And also in most cases, the lens would be placed in a medium whose refractive index would be less than that of the lens. So the lens would be placed in a rarer medium. So this kind of a lens behaves like a converging lens. We might have done this experiment in school, most of you all, where most students would have focused sun rays onto a paper. Now what is seen is, after some time, the sun rays are focused continuously, then the sun rays carry energy. So this energy is being focused on a given point in a paper, because of which this part would heat up and starts to burn. So basically, the focusing of light rays is nothing but converging the light rays from far away to a given point. That's called as a converging lens. A diverging lens means a lens whose middle path would be thinner, and edges would be thicker. And here again, this lens is most cases placed in a medium of lesser refractive index. In such a case, this lens would behave like a diverging lens. So if light ray falls on this which is parallel, these are diverged like this. Now this is called as a concave lenses. Do remember that in most cases, convex lens is like a converging lens, and then concave behaves like a diverging lens. There are instances where the property would be changed, but we will see when does it happen. But for now, assume that convex lenses are like converging lenses, and then concave like diverging lenses for now. Now to understand in further, we can look at a convex lens to be part of two imaginary spheres. We know that a convex lens would be thick at the edges and thin at the ends, something of this kind. So we can assume that this convex lens is part of two imaginary spheres. Now the question is, what is the first sphere here? Now, even though this sphere comes first and this comes again by diagram, but the first sphere is defined by that part of the sphere where light falls first, which means suppose somewhere here an object is placed like this. What will happen is light from this object falls on the lens. Now light falls on this part of the lens first. So that part of the lens where light falls first is called as the first sphere. So for a biconvex lens, this would be the first sphere and this would be the second sphere. These are very important because the entire behavior as to why is focal length positive or negative depends on these factors. So don't think that the sphere which comes first is the first sphere. Rather, it is that part of the sphere where light falls first. That's the first sphere. Center of curvature of this sphere or center of this sphere will be somewhere here. We will call this as C1, and center for this is somewhere here. We call it as C2. Similarly, we can assume that the point where the two spheres intersect, this intersection is what is called as a convex lens. But remember, we don't break space and we don't make space and break it from there. It is made this way only just for studying purpose. We assume that these are part of two imaginary spheres. The same way, if we look at a concave lens, when light falls on the concave lens, when light falls like this, since light falls on this part of the lens first, it would mean that that part of the sphere would be the first sphere. So for a concave lens, this would be the first sphere and this would be the second sphere. So center of the sphere is somewhere here, we call it C1, and this we call it as C2. So we can assume that these are part of the concave lens. In case of spherical surfaces, we add a reference point called as pole. But here, in this case, we would have two poles. A pole for this point, for this sphere, and a pole for this sphere. So we'll call this as point P1. This is point P1, P2. P1 is the pole of the first sphere and P2 for the second sphere. But the points P1 and P2 are extreme points, which means they are at the ends of the lens. So for a lens, the points P1 and P2 cannot be the reference point. So for a lens, we should define a new reference point, and that point is called as optic center. I'll define what this is in a minute. So for now, remember that for a lens, the reference point is called as optic center. Similarly, even in this case also, we would have two poles. So the two poles, each of these poles cannot be the reference point for the entire lens. So we need a common point, and it's called as optic center. Now here are some real examples of lenses. This is a convex lens as seen here. It is thicker at the middle part, and then it is thinner at the edges as seen here. So it is called as convex. When I say convex, it means it is biconvex, and here it's not visible properly, but then the middle part is thinner and the outer part is thicker. Now here is a real example of a lens where one part is convex as seen here. This part is convex and here it is plane. The convex side, because this is glass and this is air, so the convex side is facing the real medium, so this becomes plano-convex. You can look at the way light is behaving. If you have parallel beams of light falling, light rays are being converged to a given point. By definition, this would be the principal focus. Again, we take it up this in the later discussion. In this example or in this picture, we have a concave side, a concave surface, because this is the concave shape and it's towards the air. It's facing the rarer medium. So this would be, and other surface is plane. So this would be plano-concave lens. Now here are some examples of convex lens. Just learn them, just understand where it's been used. One example is a magnifying glass. This is used to magnify things, to read numbers in case of a microscope. And in most cameras, what we have is a convex lens, and then in telescope also. Again, we'll see this in later topics as to how they work there. Just for now, remember examples of convex lenses. Even a human eye contains a lens. Again, we will take up this in the later discussion. Even a human eye contains a lens, and even this lens is like a convex lens only. And also some glasses would be of convex type only. Examples of concave lenses are, it is used in glasses. So remember, based on the eye defect, some glasses could be convex, some could be concave also. So even concave lens is also used to correct some eye defects. We will see again where we use it. And even the pinholes, even here it could be a concave lens. So these are examples of convex and concave lenses. The next point what we'll learn here is optic center. We saw in the previous slides that optic center is taken as the reference point for the lens, but we didn't define what optic center was. Here we will define the optic center. Now, before going into that part, keep in mind that the entire discussion in this chapter is for thin lens. So first let's define what is a thin lens. To understand this, we'll take a case where a lens is of this kind and a lens of, say, something of this kind, or we'll make it more thinner, this kind, something like this. Now we'll take the second case. We'll take this for a minute. Now what will happen is, in this case, suppose imagine light ray is coming from far away. So we saw in the previous lecture that this light ray would refract at the surface because this is lens. Think of it to be made up of glass, and this is air, which is a rarer medium. Since in this case light is moving from a rarer denser medium, light ray would bend towards normal. So this light ray would bend like this. Suppose we call this as, say, surface A, B, D, and this is surface AED. Suppose if surface AED was not there, this light ray would have gone to a point somewhere here. It would have gone to a point like this. So this is where image would have been obtained, some point here. So at this point we would have got the image, we call it as I dash. But what is seen here is, again light refracts at this point also, because on the surface AED light is moving from denser to rarer medium. So light ray would bend away from normal, because for surface AED somewhere here would be its center of curvature. So if we draw normal here, this is what normal would be. The light rays would bend away from normal. So this light ray, instead of going like this, would bend away from normal such that this light ray would form an image somewhere here. So in this case we have two refractions. So at the point I is where the image is formed. So we'll have two refractions, but for a thin lens we assume that the lens thickness, that is, this lens thickness is very, very small compared with the distances involved. So a thin lens means it is a lens whose thickness is very, very small compared with the distances involved. I will see what is the use of a thin lens. To understand this, we'll take a very, very thin lens, something like this. So in thin lens, what happens here is, again here we'll have two refractions. First, on the first surface, something like this, light refracts and light is going towards a point like this in the previous case, but light refracts here also. But for thin lens, this distance is very, very small. So the deviation between this light ray and where it actually ends up going, this difference is very, very, very negligible because of small distance involved. So for this purpose, since it's a very thin lens, for this purpose, instead of showing two refractions like here, do understand that light undergoes two refractions only because you have two surfaces, but for thin lens the deviation is very negligible, unlike here. In this case it's a very, very big deviation. The first case, it's a very large deviation seen here. That's for a thick lens, but for a thin lens it's a very, very small deviation. So to demonstrate this, in lenses we show only one refraction. Even though there are two refractions, since the deviation is very, very small, we show only one refraction. So what books will do is, most books will show only one refraction, and they will show at the first surface. That is, if a light ray falls on the first surface like this, light refracts and things somewhere here, image is formed. This is what many books will show. This is the first case. So we are not showing the refraction at the second edge. This is what we show in diagrammatic purpose. But do keep in mind that even here light is refracting. So this is one way of showing, where we show only at the first surface. Or what some books will do is, instead of showing like this, some books may show the refraction at the second surface. That is, if light ray falls like this, they will show the deviation or refraction at the second surface like this. Even this also is acceptable. The basic point is we show only one deviation. Here we are showing at the second surface. Or some more books, what they will do is, instead of this, they will show deviation at the middle of the lens. So you can draw a line like this. You can think of a line drawn from here to here. So what books will do is, some books will show the deviation or refraction at the center of the lens through this point. They'll show like this. Even this also is acceptable. So the point is, whether you draw it like this or like this or like this, we are showing only one refraction, either here or here or at the center, not two refractions. This is true only for a thin lens, not for thick lens. You'll be wondering what this line is. So this is called as principal axis, which was defined earlier also in the previous lecture. In case of spherical surfaces, we had a imaginary line which is passing through the pole and center of curvature. That is called as principal axis. Now coming back to definition of optic center, we haven't defined it. So by definition, an optic center is defined as the point which lies on the principal axis through which the light ray moves undeviated. Which means, if light ray falls on any point, as seen in the previous cases, if light ray falls at any point, it falls here, or it falls at any point, let's point here or here or here, light undergoes deviation. But there's one point in the lens where when light falls on the lens, it doesn't go deviation. You can think of this diagram to make more sense out of it. Suppose imagine that light falls like this. Light falls at this point. It undergoes deviation. Light would be deviated and somewhere we get an image. If light falls, say, like this, it again undergoes deviation. But if light falls at this point, this light will not deviate. It just moves as it is. So this point here is called as optic center. So optic center is that point in the lens where the light rays moves undeviated. It's called optic center. The next point is very important, which is called as principal focus. Do remember that whether it is mirrors, spherical mirrors or spherical surfaces, by definition, focus would be a point where the light rays converge or appear to diverge, whether it is reflection or refraction, provided the object is at far away or it has infinity. So to define focus, we can say, in case of spherical mirrors, we define focus by telling that it is the point where the light rays converge after reflection. In case of a concave mirror, the light rays would converge after reflection. The point where they converge, this point where they converge after reflection is called as focus. In case of a convex mirror, they appear to be diverging. So even here, light ray falls and this falls, it will diverge like this. So if we draw them backwards, these appear to come from a point. So this point appear to come from, this point is called as focus. So in case of spherical mirrors, the light rays would actually converge or appear to diverge from a point after reflection. That is called as focus. But the point here is the light rays are coming from infinity. In case of lens, it is refraction. So you can think refraction as the process here. In case of a convex lens, what is seen is, as seen here, the light rays are parallel to themselves and to principal axis. These light rays, after refraction, meet at the point. These light rays would converge at a point. This point is called as principal focus. While in case of a concave lens, what will happen is, for a concave lens, light rays are parallel to themselves like this, and one more here. These light rays would be diverged like this, so these light rays cannot form an image on this side. If you draw them backwards, it appears as if these points would come at a meter point here. They appear diverged from this point. So this point is called as principal focus. So it can be a point where light rays actually converge in case of a convex lens, or it can be a point where light rays appear to diverge. That is, if you see from this side, then you find that these light rays are coming from a point. So that point is called as the focus. So a focus is defined as a point where all the light rays coming parallel to the principal axis either actually converge, as in case of a convex lens, or appear to diverge from it. That's called as a focus point. To be more precise, this focus is called as F2, which is called as image focus, because since we have two surfaces, we have two focus points. To make sense out of it, think of a case where we have a lens, and like this. You all might have learned in high school that if we place an object at a given point, there's a point in front of the lens where the object is placed. These light rays, after falling, would become parallel to the principal axis. So it basically means that these light rays are tending towards infinity. So this point here is called as object focus, or it's called as F1. To understand this, imagine here we place a plane mirror in front of this lens. Then what will happen is, by principle of reversibility of light, these light rays would be reflected back, and these light rays would trace the direction back and go to the object only. So from this side, you see, from this side, it's like light coming from infinity, and this would be the focus point. So in case of lenses, we'll have two focus points called as object focus and image focus. The same way, even for a concave lens also, we'll get 2 points called as image focus, and here we get a point which is object focus. Even this is a virtual point. This would be F2, this is F1. But by convention, whenever we say about focus, it basically means it's only the image focus. It's only this point. So don't get confused here. Whenever I say focus, it's the image focus only. Therefore, the distance between the pole to the focus point, this is called as focal length F. As we saw in case of a plane mirror, we can have infinite focus points. That is, based on how light is incident, we can get infinite focus points. So if you put a plane here, then imagine light ray is falling like this. It's falling like this. So even this light rays would refract and meet somewhere here. So even this would be a focus point. So do remember, based on the orientation, but remember here, these light rays are parallel to themselves. So U is tending to infinity. In such cases, these light rays would meet at a point. Even this is called as focus. As we saw in case of spherical mirrors, there will be infinite focus points, and all these points are present or contained in a plane, and that plane is called as focal plane. It's called as focal plane. So focal plane is a plane which contains all the possible focus points, and this plane would be perpendicular to the principal axis. Of all the focus points, there is one point which is most important, and that point lies on the principal axis. That's called as principal focus. So keep in mind that principal focus is one kind of the focus point which lies on the focal plane. So from now on, whenever I say focus, it is only the principal focus, or more precisely, it is the image principal focus. Again, here we have the Cartesian sign convention, as we have studied in case of spherical mirrors as well as spherical refracting surfaces. The first convention here is that all distances are measured from the optic center. It is same as in case of spherical mirrors or spherical refracting surfaces, where the reference point was pole. In this case, the reference point is optic center. So the first point is all distances are measured from the optic center. The second point is distances measured in the direction of incident ray are taken as positive, and distances measured in the direction opposite to that of incident ray is taken as negative. Now these are the same points as what we have learned in case of spherical mirrors or spherical refracting surfaces. Third point is heights above principal axis is taken as positive, and heights below is taken as negative. So with this in mind, we'll just recap what would be the focal length in case of a concave and then convex lens. As seen here, by sign convention, the reference point would be the optic center, which is here. So this is the reference point, we'll call it as C. Now recall what is optic center. An optic center is a point through which the light ray moves undeviated as given here. It's optic center. Now in this case, by sign convention, light is moving from left to right. So we are moving from left to right. By sign convention, the distance between C to F would be positive, because you're starting from the point C and going to the point F. We're going like this. In this case, F is positive. So for a convex lens, F is positive, or more precisely for a converging lens. Just learn this. For converging lens, F is positive. While for diverging lens as given here, light is moving from left to right, but we are moving from the optic center to the focus like this. We are going like this. We are going from C to F in this direction. Since we are going against light direction, by convention, the focal length for this would be negative. So for a diverging lens, F is negative. So remember this also. Now we'll see what about C1 and C2. We saw that this is a part of two spheres as given here. You can think of a convex and a concave lens as part of two spheres. So in that sense, it is very clear from here that by sign convention, this C1, or the distance from this point P1 to C2, or this point here. Just read out this part. So we saw that this would be the first sphere and this is the second sphere. For the first sphere, this was the pole, and for second sphere, this was the pole. But for thin lens, these 2 points are very close to each other. So we'll take the reference point as C itself. That's a reference point. Do remember that it's drawn very big here, but these 2 points, which are the poles of the respective spheres, would be close to the point C only. So distance from here to here is called as R1. So by sign convention, light moves from left to right. So here R1 would mean distance from C to C1, or from here also the same meaning. So for a convex lens, R1 is positive and R2 would mean distance from the pole of the second sphere, or from C to C2. This distance, this would be negative because we are going against the light direction. So for a convex lens, R2 would be negative. Similarly, if you look at a case of a concave lens, then this would be R1. So here R1 is negative and here R2 is positive. So these are the sign conventions. Thank you.